I'm not going to repeat some of the notation, but I'm going to kind of briefly outline what was going on with this. If we have a linear transformation phi from E to E, and is phi cyclic with minimal polynomial, Q of X, which is X R plus A R minus 1, X R minus 1, plus A1 X plus A0. Then this is phi cyclic with this minimum polynomial if and only if the dimension of E is equal to R. And relative to some basis, the matrix of transformation looks like this. Okay, so let me kind of illustrate to you why this is true. In fact, in this case, your E is let me illustrate why this matrix works the way it does. Basically doing multiplication this way. This matrix is this vector is V, right? So what happens when you multiply this by this? You get correct. If you multiply this, I get 0, then I get 1 and the vector 0, right? So I'll basically move the one step to the right, and this is phi of V. Correct? Now, what happens when I do phi of V and then do the transformation to it? Now I've got this, right? So this gives me 0, 0, 1. And it marches at one step to the right, right? Everybody okay? Now, the last question you might ask yourself is, okay, self, what happens if I keep this up? What happens to phi to the R minus 1? What happens to this one? Well, this one is minus A0 minus A1 minus A2 minus AR minus 1. Correct, corresponding to that last row in the matrix. And what's another name for this? Well, another way to write this, of course, is this here. Right, because the 1, 0, 0 is just V. The 0, 1 and the rest are zeros is phi of V, and so forth and so on. Minus AR minus 1. Anybody see what this is? Notice that this polynomial is x to the R minus A0 minus A1 x minus 2x squared minus AR minus 1. Correct? That's right. This is what it's supposed to be. This is actually phi R. Right. Which is exactly, because really what this is doing is this is doing the job of phi with respect to the basis. So when I apply this matrix, this should be phi RV. And that's why you need this last row that corresponds to this minimum polynomial. Am I okay? I did give you one more theorem that I want to kind of at least give you the gist to why it's true. In the special case, has minimal polynomial or form. Let's see, what do I call this? Q of x equals x minus lambda the r. Then we can write this in this way. That was the last kind of corollary that I gave you all last time. Why does this work? Well, excuse me, let pitchfork so I'm going to adjust this. Notice that if Q x minus lambda r is the minimal polynomial for phi, then x to the r is minimal polynomial for pitchfork. And so for pitchfork, what you'll have is you'll have the rational canonical form that looks like this. Because this block corresponds to the polynomial x to the r. So pitchfork will have this with some basis, right? So the bottom row is going to be all zeros in this case. And now phi, our original one, is pitchfork plus lambda I. So all you got to do is add the lambda down the diagonal. And there we go. But notice, you can't always necessarily get things in terms of powers linear. Like, for example, if you have the polynomial x squared plus 1 comes up over the reals, you cannot write that in a product of linear polynomials. Okay. Any questions?
How did you go from psi to phi for differences?
Oh, using this right here, because pitchfork plus lambda I is equal to otherwise. Okay, so let's get our hands started here. Let me look at some examples. Okay, now let's suppose, now you might just go with me on this because the beginning of this example might seem a little bit disingenuous because, well, I'll show you why. Suppose we have a linear transformation. Suppose f is equal to q. So I've got the field of rational numbers, that's my playground here, and I have a vector space over Q. Vector space. With and B is a linear transformation, from E to E. Suppose that it has the invariant factors. And let me just kind of list them here. X squared plus 1 squared, x minus 2 squared. And for your convenience, I've multiplied this out. X6 minus 4x5, 6x4, I think. Minus 8x cubed. Squared. Minus 4x plus 4. So there's one of the invariant factors. And I've got another one, x squared plus 1, x minus 2. We've got that invariant factor there. And finally, x squared plus 1. So find canonical forms. So that's my basic construction. So I've got 3 invariant factors. Now, I'm going to do what I call the rational canonical form. Rational canonical form keys off of doing just the invariant factors. By the way, the vector space C, what's its dimension? It is 11, because this is going to correspond to a block, a subspace of dimension 6, another one of dimension 3, another one. So the entire matrix should be 11 by 11. So this is an 11-dimensional vector space. Now, the way I find the rational canonical form is I just build one of these promised blocks, and I don't know if that's going to be big enough. I build one of these promised blocks from every one of the invariant factors. So here's the first invariant factor. So let's build the 6th block. 3, 4, 5, 6. Right. And then run this in reverse order. Minus 4, 4, minus 9, 8, minus 6, 4. I am not going to put 121 entries into this matrix because I'm a lazy man. Everything that I don't write is a 0. Okay. So I've got this first block, this 6 by 6 block. And then I get a 3 by 3 block down here corresponding second invariant factor. By the way, you can put these blocks in any order you want. It doesn't matter. They're all conjugate of each other. So now I get a 3 by 3 block. And then this thing here, 2 minus 1, 2. And here, finally, a 2 block. And minus 1. Fill the rest in with zeros. and this is the rational canonical form for this linear transform. Everybody okay with that? Primary rational canonical form. What's the difference between rational canonical form and primary rational canonical form? Primary rational canonical form does the same dang thing, only instead of using the invariant factors, it uses the elementary divisors. So let me go back here and pick out the elementary divisors. So what I'm going to do is I'm going to pick out the prime powers. And I've actually written this in terms of prime powers. Notice x squared plus 1 as a polynomial over Q is actually an irreducible polynomial, so it's prime. So I basically got two primes going on here. I've got x squared plus 1, I've got x minus 2, right? So let me list them according to the prime. So my elementary divisors are x squared plus 1 squared coming from this, x squared plus 1, and x squared plus 1. Right. And my elementary divisors off of here are, and by the way, I'm going to write this one out here. This is x4 plus 2x squared plus 1. So this is one block here. And I've also got x minus 2 squared, x minus 2. That's it. And this one here is x squared minus 4x plus 4. And I'm going to need to have it multiplied out for make the blocks. Notice I've got the same sort of total block size in the following sense. Should have 4 block and a 2 block and a 2 block. So that comes to 8. And a 2 block and a 1 block. So that comes to another 3. So that's 8. So this will be smaller blocks, right? You don't have that big hunk in 6 block, smaller blocks, but more of them. Right? So what does this one look like? This is the primary rational canonical form. Well, let's see here. Same deal. If I don't write the entry, it's a 0. Okay, I'll start with the 4 block, which is the biggest one here. And finally, I guess that's minus 1, 0, 2, 0. Right? Yeah, it is minus 2. Okay, so that's the big block. Now I've got a couple of 2 blocks that look the same. 0, 1, minus 1, 0, 0, 1, minus 1, 0. That takes care of these 2. Okay, now I've got 2 of these things to take care of. I get another 2 block that looks like this. 0, 1, and I guess minus 4 plus 4. And then finally, the final 2 block is just, or the final block is just 2. Will be 3, 4, 5, 6, 7, 8, 9, 10, 11. Good. Everything else is zeros. So actually, these 2 matrices are actually conjugate for each other. It's just choosing to write it in this way with the invariant factors as opposed to writing it this way in terms of the elementary divisor. And that basically that's the same thing as saying Z6 is isomorphic to Z2 some Z3. Which way do you prefer to write it? Okay. What about the Jordan form? The one that came from the corollary. Over Q, this has no Jordan form, because the problem is when you look at your invariant factors, they are not powers of linear. You're stuck. The x squared plus 1 is killing you, right? But there is no Jordan form over Q. but over in fact, all you need is a field that's just big enough to contain I, because you need to split this down. But the invariant factors are well, actually, let's do the elementary divisors. Right here, x plus I squared, x minus I squared, x plus I, x minus I, x plus I, x minus I. Right, each one of these x squared plus one splits up into x plus I and x minus I. So this is one prime here, the x plus I ones, and here's another prime, so we've got the powers of that. And these elementary divisors stay the same. So I should have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Good. The Jordan form for this over a bigger field where you can break down x squared plus 1. For example, C, but it could be a smaller field. Let me make a quick note over here that of course x plus I squared is x squared plus 2ix minus 1, and x minus I squared is x squared minus 2ix minus 1, and x squared minus x minus 2 squared, a reminder, is x squared minus 4x or 4. So now let's build our thing. Right. So if you look at the block for x plus I squared, actually I didn't even need to multiply that out. I'm totally deranged here. But the step in what I didn't go into today, I'm not thinking. So let's just go down these blocks in order. And I'll stick to the same prime. So this has eigenvalue negative I. So there's the block corresponding to this. And then the block corresponding to the next one. The next one. These are all just one blocks. Now the block corresponding to this one is I, 1, 0, I. And then I guess I got two more I's, two more little one blocks. And finally, I just have to deal with these two. I got a 2 block, let's see, 2 and a 1 block. And there it is. That is the Jordan canonical form in all of its glory. Notice this one is kind of really neat because this thing is dang close to being a diagonal matrix, right? It's just got 3 1s on the upper diagonal, right? So the Jordan canonical form is often the easiest to kind of wrap your head around because you've got zeros everywhere except the main diagonal, perhaps in the super diagonal. Everywhere else is 0. Okay. Okay, so far. Okay. Everybody see how to put that together? What should your big complaint be at this point? Come on, you all refuse graduate students. You certainly must have some complaints. I think something that's a little disingenuous about my example is I walked up to you like some kind of, slickster snake oil salesman and said, oh, look, I've got this thing with 3 invariant factors, right? Yay. Well, it's awful easy when I've listed polynomials, right? How do I get this in the first place, right? What if I walk up to you on the street and I give you a linear transformation or matrix and whatever, you don't know the linear or you don't know the invariant factors. How do you get these? Well, guess what? I've got a theorem for you. I'm going to do this without proof, and I'll tell you how to. I'll work it. I'll do an example. So, theorem. Let A be an n by n matrix over the field K. Where K is absolutely clear. So suppose you have an n by n matrix over the field. The matrix of the matrix A minus X I N is equivalent via elementary row and column operations over KX via row column operations over KX. When I say over KX, what I mean is I can invert any non-zero element of K, but polynomials I can't divide by X. I can't divide by any polynomial of degree 1 or greater to a diagonal matrix. With diagonal entries F1 divides F2 divides Fn, where Fi is in Kx. So these are polynomials or perhaps constants. The non-constant polynomials Fi's are the invariant factors. And Fn is minimal polynomial. And the product of all of them is the characteristic polynomial. So the degrees of all these added up should add up to n. All right. So you can, if I walk up to you on the street and give you a matrix, you can basically what this is just set up to find the eigenvalues, right? So you do that, but instead of going through and doing the determinant, you row reduce the matrix, and you can always row reduce it. Actually, because this is a Euclidean domain, you can always reduce this to a diagonal matrix where the diagonal entries are non-zero polynomials, and they could be constants. It could be 1. And the non-constant ones are the invariant factors. The product of all of them is the characteristic polynomial, should be. And the largest one, the one in the lower right corner, should be the minimal polynomial. So let's actually do this. Look, I'm not actually, I think maybe this will be the, I'm going to give you one to work for yourself. Just fun. Let me do this one. Let A be 5 minus 3, 12 minus 7, 6, 6, minus 3, 2. Okay, so what I'm going to do is come through here. So what I want to do is find the invariant factors for this matrix. So just do this. And now just row reduce. So by the way, I can invert any non-zero element of K. And I can do the elementary row and column operations. Row and columns are good. I just can't divide. I can't divide by 5 minus X. Right? I can't divide by any polynomial of I can't divide by 0 or any polynomial bigger than 1. That's what I mean by over this over Kx. So let's kind of go through this. The first thing I did is I divided I guess the top and bottom for each. But I should say equals, but should have, it's equivalent. Next step, I'm going to use this -1 to nuke everything below it, right? So in particular, my next step, 5 minus X over 3 minus 1, 1. I'm going to multiply the top row by -7, -X, and add it to this row. All right. So basically, what I'm trying to do is kill this middle entry, which I'm very proud of myself for doing. Multiply -7, -X, and add to the bottom, so I get -1 minus X here. And I've got to multiply this by -7, -X. That's going to give me X squared plus 2X. We multiply it out, and it's going to give me like -35 over 3 plus 36 over 3 is 1 over 3. Am I okay with it? And then I'm going to just multiply the top row by -1 and add it to the bottom. So that's going to give me a 0 here. That's going to give me a -1 minus X over 3. And let's see, times -1 and add to the bottom. So that's going to be X minus 1 over 3, or I'm sorry, X plus 1 over 3. Like that. Everybody okay with that? So these are just rubber. Now, the next thing I'm going to do is I'm going to use this 1. I'm going to do column operations. I'm going to wipe these clean, right? Zeros and zeros, right? And so now I can rearrange this a little bit. So this is, I'm going to rearrange some of the rows and columns just to organize this a little bit. So basically, I'm moving this row over here and changing the sign. I've got zeros here around the top. So in the middle, I've got X squared plus 2X plus 1 over 3 -1 minus X, X plus 1 over 3, and -1 minus X over 3. I find this really obnoxious, don't you? So you know what I'm going to do? I'm going to clean this up a little bit more. I'm going to multiply this column by 3 because despite the fact I'm an algebra, I really hate fractions. So this is X plus 1 squared, X plus 1. And I'm going to multiply this row, I'm sorry, this column by -3. Anybody see a good move for me now? How about -1 times this column plus this column, right? Everybody, that's looking really sexy to me because I'd love to see this disappear. So this actually becomes 0. And let's see, this is going to be 3x plus 3 still, x plus 1 still. I'm not messing with this. So -1 times this plus this, I get a big fat 0, so that's good. And this is going to be x squared minus x minus 2. Everybody okay with this? Now what? Right, now I've got everything eliminated here. This can kill this, right? Just multiply by -3 and add. So I'm getting like all excited about this. So this is now 1 0 0 0. All I have to do is put this in a different order, right? I can just change this. Flip these rows, flip these columns, and there's also a very important thing to notice. What's true about this? This is actually, and it better be. Otherwise, I've screwed up the computation because it needs to divide as you go down. So for this particular matrix that we started with, that I've erased, of course, your invariant factors are x plus 1 and this other one right here. So now it's actually this one, the invariant factors are all linear products of linear polynomials. So for this one, you can figure out the rational canonical form, the primary rational canonical form, and the Jordan form. Right? By the way, let me point out, it is sometimes possible for some of these forms to be exactly the same. For example, if there's only a single prime power polynomial, then your primary and your rational canonical form will be the same. Everybody see how we did that? Okay, so let me give you an exercise. Try this, and I'll tell you what I think the answer is too. So on your own, give this a try. -1, -1, 5, -3, -2, 11, and 3, -2, 3. And I'll tell you what I think I got. I only got one invariant factor for this one. And I got x minus 2 times x plus 1 squared. That's what I got. But check me on that. So now I have given you the tools that you need. If you have a matrix, this trick will always work to find your invariant factors. And once you get your invariant factors, you can do all the canonical form, rational canonical, primary rational canonical, and the Jordan form if it works. And that is a good sort of prelude into, so now that you've warmed up on that, this will help you with your next assignment, which I'm going to say something about now. Let's go with the magic projector. So if you do this little trick here, minus x minus x minus x, and do the reduction, you can get the. Yeah, I was just gonna see how much pain you all can endure, right? Yes, it will work. Please do not do it, right? So I want you to find the reason, don't let the number of points this is worth intimidate you. I don't think this is a terribly hard assignment, but it'll help you get your hands started figuring things out. I want you to find the primary rational canonical and Jordan canonical form, if possible, for following matrices over Q and C. That's basically 3 points apiece, right? Because you got 3 canonical forms for 2 fields, right? Subtract x down from the diagonal and you can work it out and get the characteristic or get the invariant factors. Please don't do this by hand. How many of you have used Maple, Mathematica, any of these things? Right. What you want to do with this is, oh, and by the way, I've got to grade this. I don't want to be grading. You know, I just really don't. So I trust you. Do the software and figure this out. What I want to see on your homework is write down what the invariant factors are and then use it. The way to do this is use some software, right? Do what I described here with the minus x and find what they call the Smith normal form. I'll show you how to do it in Maple, right? But there are other ways to do it. And once you find those invariant factors, it becomes much easier. By the way, I'll give you a hint. I hate to spoil the surprise, but I will anyway. This matrix, horrible looking, right? If you cube it, it's 0, right? Doesn't look like it at all. And I would not advise that you try to do that by hand either. But if you cube this matrix, you should get 0. Find a canonical form for that, kind of going through what we did here. So suppose I give you the following characteristic polynomial. Remember, the characteristic polynomial is the one you get the eigenvalues for. The characteristic polynomial, all the invariant factors should multiply together to be this, right? So what's the size of the matrix in number 2? 06, actually, right? Yeah. Because it's 6 degree, it's a 6 degree polynomial. If that's a characteristic polynomial, it's got to be 6. Agreed? Mm-hmm. I have not told you in this what the invariant factors are, right? Because it could be different things. There's not enough, just the characteristic polynomial is not enough information to tell you what that matrix is. Sometimes you can get away with that for like small matrices, right? But the bigger the matrix, the more degrees of freedom you have, and the more ambiguous the characteristic polynomial is going to be. So find me all of them. What are all the possibilities here? And finally, this kind of makes me think like a Matt Macaulay problem, sort of, because it's group theory. You know what GL2Z2 is, right? It's 3 by 3 matrices with entry 0, 1, right, in Z2 that are invertible. Right. One of the interesting things of this is probably the smallest simple group that you may not know is a simple group, right? The small simple groups that you think of that aren't abelian are like what, A5, right? And then A5 and then A6. Anyway, so this is the second smallest non-abelian simple group. Right? This is actually, it's got 168 elements in it, I think. Anyway, so you only need to consider the invertible ones because this is a group of invertible matrices. Find the number of conjugacy classes in G and a representative of each class. This is actually an application of these canonical forms. So think about that a bit. Any questions on that? Okay. Oh, turn that off so don't confuse everybody. Oh, by the way, before I forget to mention it, we've got a job talk today, and at 11, well, a little bit after 11 o'clock, which I am going to. So if you wanted to see me during that hour, just let me know, and we can certainly work out something today. Just let me know after class. What you want to do to find the invariant factors. So actually, these are the two matrices right here that I put on the analogous homework set last year. They were both 5 by 5. I made that 7 by 7 one for you guys because I thought it was really fun. But anyway, so What you can do is just enter this into Mathematica, Maple, and what I would do is find the Smith normal form. That's not the exact command, but it's close enough. And the Smith normal form is exactly that form that I got with the 3x3 matrix, where it is a diagonal matrix with some ones perhaps in polynomials down the side. So basically just get some software to do this for you. I did this for both of these, and here's what I got. For this one, the Smith normal form of this matrix, and we'll probably continue this example next time, I guess, was 1, 1, 1, 1, and all zeros everywhere else. And the beautiful polynomial x to the 5 minus 6x4 plus 16x cubed minus 32x squared plus 48x minus 32. Which actually, so I did the Smith normal form, it's all zeros, one side of that. So this actually has a single invariant factor. And this one is actually x minus 2 cubed times x squared plus 4. For this first one here. And for the second one, what I got was 1, 1, 1, x minus 1, x4 minus x cubed. For this one right here. And notice that, again, it's kind of a good gut check because it should divide all the way up. All right. Let's look at the second one. Notice the first one, whether or not the first one has Jordan form depends on the field again. So over Q, no. Over any number with the square or any field with the square root of -1, it will. So, well, in our remaining 2 minutes, which do you want to do, the first one or the second?
The first.
You want to do both? Okay, so first, rational canonical form. That one is, in a certain sense, kind of easy because there's only one invariant factor. And along the bottom, I've got 32 minus 48, 32 minus 16, 6. So there's only one block for that. Right? What about the primary rational canonical? Well, this time I've got basically 2 primes, x minus 2 and x squared plus 4. Those are the 2 relatively primary polynomials. So I'm going to have a 3 block for the x minus 2 squared, I'm sorry, cubed, which is x cubed minus 6x squared plus 12x minus 8, I think. I did that right. And so 8 minus 12, 6. And then I'm going to get the x squared plus 4. That's the other elementary divisor. It's the different prime. There's primary rational canonical. Okay. No Jordan form over no Jordan form over Q, but over C, x squared plus 4 is x plus 2i times x minus 2i. So now the Jordan form, well, you're going to have this block here. And you also have x minus 2. So you're going to have 2, 1, 0, 0, 2, 1, 0, 0, 2. There's the Jordan block for this. You're going to have 2 smaller Jordan blocks, just 1 by 1. Is that clear to everybody? Y'all see how we work that out? Yes.
So, like, how does that change? How does our like rational canonical form, how would that change if we would be over C? It would still be the same.
Oh, the rational canonical form. Let's see, over C. Yeah, because I mean, the elementary divide, the invariant factor here, it is what it is, right? So
So it would just be the same.
it would be the same over C. And the primary rational canonical form, I need to, one thing about the primary rational canonical form will also be different. So I'm glad you said that. This is Jordan canonical form, the primary rational canonical form, because now what you have is you have the elementary divisors are x minus 2i, x plus 2i, and the big chunk, the x cubed minus 6x squared plus 12x minus a. So it will be different over C, because this block will be the same. 8 minus 12, 6. But then this block right here, these are not prime powers anymore. This is private of let me see here. Yeah, because I'm doing this in prime powers, that's right. So this is 2i. Oh, yeah, over the complex minus 2i. Because over the rationals, this is an irreducible, right? However, over the complex, it's a product of 2 relatively prime primes. So you have to break that down further. So good call. Any other questions? Other questions? All right. Well, how about you, Alec? You okay? All right. Well, think about doing that. Okay, good. Think about doing the math for all thing today. And other than that, y'all have a good weekend. I'll have your homeworks caught up graded pretty soon. If you're having trouble finishing up this one, just let me know. And have a good weekend.